So there's going to be one last tweak we make to our conservation of energy equation. We're still going to think about, how much work different forces are doing, but now I want to recognize that there are certain types of forces that do something very, very specific to our system. And those types of forces I want to talk about are called dissipative forces. So dissipative, to dissipate something means to take something away or to make it smaller. So forces like kinetic friction and drag are dissipative forces because they take energy out of the system, but they do something very specific. They don't just take energy out of the system like you would do if you pressed, in the last example when the kid was swinging towards you and you get pushed a force in the opposite direction the object was moving, you did negative work. You took energy out of the system, that's true, but that when you took the energy out of the system, it's different than when kinetic friction takes energy out of the system. Because when kinetic friction takes energy out of the system, it does it in a very, very specific way. It converts that energy into thermal energy. So when there is kinetic friction, so let's say you're dragging this crate across the floor and there's kinetic friction. Some of the work that you are doing, you're putting energy into the system because you're pulling to the right and the object is moving to the right. So some of that work that you're doing is it's not being used to make this go faster, because let's say you're pulling it at a constant speed. You're pulling to the right, it's moving to the right at a constant speed, you're doing positive work, but the energy of the system is not getting bigger. Where's that energy going? Well, it's getting turned into thermal energy because the floor is going to get a little bit hotter. Whenever you have friction, the surfaces where there is friction get a little bit hotter. Or sometimes they get a lot hotter depending on how much friction there is. So that's an example of the energy of your system being turned into thermal energy when something gets hotter. And dissipative forces, that's what they do. They convert energy into thermal energy. So our system, in this case, when you're doing positive work, you would expect the kinetic energy of your system to get bigger. It doesn't, because energy is being dissipated. It's being converted into thermal energy. Things are getting hotter instead of this moving faster. Okay, so what I'm going to do is go back to my full conservation of energy equation, and I just want to separate out how much work is friction doing, because that work, something is very specific is happening with that amount of energy. It's being turned into thermal energy. So we're going to define a term. We're going to talk about the change in the energy due to dissipative forces. That's what this term here represents. It's just an amount of joules. It's just a certain number of joules. And I'm just saying how much energy is leaving the system because of the dissipative forces. Most of the time we're talking about kinetic friction. So how do I quantify that? Well, I'm going to calculate how much work does kinetic friction do. And that's just going to be equal to the force that kinetic friction is exerting times the distance that the friction is acting over. But I'm going to take the absolute value because the work that kinetic friction does is always negative, because kinetic friction always goes in the opposite direction that the object is moving. I want to define this number to be a positive number. That's just what we're going to do. We're going to say I'm defining this as a positive number. How much energy is leaving the system because of dissipative forces like kinetic friction. So I want this to be a positive number. So I'm going to take the absolute value of how much work kinetic friction does, because this is always negative. Okay. So again, this is the energy that's lost it's lost as heat due to friction. Okay. We define this as a positive value. So because the work that kinetic friction does is always negative, I need to take the absolute value of that work. And how do we calculate the work done by friction? It's just equal to the force of friction times the distance over which friction is acting. That's how we always calculate work. Work is always how big is the force, what's the distance over which the force is acting. Okay. So we want to include this term here in our conservation of energy equation. So I want you to think about which one of these is going to be the correct way to include this term, knowing that this term is always a positive value. So press pause and read through this and think about it and choose an answer. Then when you're ready to go through it again, press play. Okay, well, I want this value, which is a positive number, to decrease the total amount of mechanical energy. So I'm going to put it on this side of the equation, right? Because, the bigger this number is, the less energy I have left over as mechanical energy. So we're going to put it on the right here. Okay, again, this is a positive number. So this, now we have our total complete conservation of energy equation. This is the equation that you can use in every single problem, and it will always work. Sometimes this might be 0, sometimes this might be 0, but this equation is always going to work. I've changed this. I used to write W non-conservative here, but now I really want to emphasize that this is the work done by not just non-conservative forces, but very specifically external non-conservative forces, forces that are external to our system that are non-conservative. And I'll explain that in the next examples. But just to remember what each of these terms mean. This is external work, so forces on the outside of our system. So these are forces that are non-conservative, that are doing work, and they have to be external to our system. This is the increase in thermal energy. So things are getting hotter due to the work done by dissipative forces like friction. And remember, really, what are we talking about here? We're talking about external forces except gravity and springs, and now except for friction, because that gets taken care of here. Okay, this is just the work done by friction, but it's the absolute value of it. So this is the equation we're going to use in all of our problems now. And then we can say, for isolated systems, isolated means there are no external forces. For non-dissipative systems, non-dissipative means there's no friction. So if our system is isolated, this term is 0. If our system is non-dissipative, this term is 0. For isolated non-dissipative systems, mechanical energy is conserved. That means Ki plus Ui equals Kf plus Uf. That's only true when this term is 0, there's no external forces, and when this term is 0, there's no friction. But if we do have external forces, we know what to do with it. If we do have friction, we know what to do with it. And we'll see how to deal with this full equation in the following examples.